morning, ladies and gentlemen. My name is Nadav, and I'm a student in Norberto's lab. And today I'd like to present my project to you, which is a probabilistic model predicting retinal ganglion cell responses to natural images. So, why natural images? Most studies have been using artificial images because we can control their properties very well. However, our visual system is evolutionarily designed to encode natural images, which present far more complex statistics. And in order to understand how we see what we see, we need to have models that can predict the responses to those images. So in my experiments, I'm presenting sets of natural images and artificial white noise images to retinas from rats, and I record the retinal ganglion cell responses using a multi-electrode array. So what makes the responses to natural images unique? If I present a sequence of natural images to a retina and I record the responses over 4 trials, the first thing you can see is that the responses are probabilistic. So they change, they vary a bit between the trials. Moreover, there is certain trends that are maintained between the repetitions, like the quiescent period at 0.6 and the bursting of spike right before and after the quiescent period. If I do the same with artificial images, If I do the same with artificial images, you can see that the probabilistic nature of the response remains, varying between trials. However, the magnitude of the response is generally lower compared to natural images, and it's more frequent. So I get more frequent activity. So one model that people like to use to predict responses to images is the linear nonlinear Poisson type model. And the way this model works is I take an image, I dot product it with a spatiotemporal filter, I put the product through a nonlinearity to estimate the average number of spikes, and I randomize it, I create variability through a Poisson process, which gives me the estimate of the action potential generated by the image. However, we know that those models don't work well for natural images, and let's see where the model fails. So looking at the spatiotemporal filter, this is the filter calculated with using a spike-triggered average method, and for natural images, you can see that this particular RGC likes dark objects turning into white presented at the center of its receptive field, which means that this is an on-type cell. It likes changes from dark to bright. And when I repeat it with this calculation with artificial images, the trend remains where the cell, you can still see the trend where the RGC likes dark objects turning into bright objects present at the center of its receptive field. So in conclusion, the filter is not the problem. The filters work the same for natural and artificial images. However, looking at the nonlinearity, by taking a sequence of images, dot producting them with the filter, I can get a single value, which I call the image projection, that gives me an estimate of how good this image is in eliciting spiking response. And if I do it for all the images presented to the RGC, I get a cloud of points that, as you can see, for increased image projection value, the likelihood of the response increases. Now, I can calculate the maximum likelihood estimate of those data points, which is what I would use to fit a nonlinear function upon. And for artificial images, you can see that the estimate captures the bulk of the cloud pretty well. So it rises up to around 0.75, and it goes through the middle of the cloud. However, when I do the same thing with natural images, the estimate rises minutely, and it does not capture the bulk of the cloud, it only captures those highest image projection points. So the nonlinearity is the problem when I try to predict responses to natural images. So we had to think about the solution. And looking at the responses, seeing that the responses change between the trials, we thought that aiming to predict the probability instead of the absolute or average response would be more correct. So the first stage in developing our model is binning the image projections value into bins and calculating the probability of generating any spiking response for the image projection bins. And you can see, for increased projection values, the probability increases as well. And I can do a bit better by generating a three-dimensional probability histogram showing the probability to fire increased number of spikes for the same image projection values. Now, this already starts to look like a probability distribution. And we needed to think what type of probability distribution might fit this data. So we went back and looked at the structure of the retina, and I'm sorry about the structure of the retina, and we know that in the retina, many bipolar cells converge on a single ganglion cell. And the outputs of those bipolar cells sum, creating a pre-firing signal. And when this pre-firing signal crosses a threshold, spike firing occurs. And this conforms very well with the central limit theorem, which states that the mean of a sufficiently large number of independent random variables will be approximately normally distributed. And if you look at the normal distribution function, it means that the pre-firing signal is distributed about the mean, and there is a threshold above which those values generate action potentials, firing. So implementing this function into our model, we got excellent fits. As you can see, the normal distribution fits the histogram very well, cutting them through the middle, essentially. Now, in this function, we have three parameters, mu, theta, and sigma. And theta is the intracellular value, the threshold above which I generate spike. And I cannot know that because I'm not recording intracellularly. But I do know that mu gives me the distance to theta. And because I can calculate the probability, because I have the probability values, which are the area, the gray area, I can know mu using an inverse Gaussian complementary function. So I can calculate the mean of how the mean changes for the distribution. And the only free parameter for this optimization is sigma, the standard deviation. Now, some of the cells, a few of the cells we recorded from, presented a more complex behavior where the probability to fire intermediate spiking magnitudes was greater than the rest. And we hypothesized that this is because of a refractory period, which limits the ability of the cell to generate a high magnitude firing. So we created a spike limiting function that has two free parameters, A and K, A controlling the maximal firing rate, and K the sensitivity to saturation. And we combined it with the normal distribution using a change of variable operation to generate a probability distribution that is not necessarily symmetric about a mean. And using this to fit our data, we saw that this function fits the data very well as well. So you can see the fit in the black line rising and falling, capturing the spike saturation. And we were able to get those fits only two free parameters, the K, which controls the sensitivity to saturation, and A, which controls the maximal firing rate. So just to show how robust our model is, this is an off-type cell. You can see a bright center changing into a dark center, and it is not sensitive to spike saturation, meaning it falls monotonically for increasing spikes fired, and our data still captures this very well, and it is stimulated with artificial images. So in essence, our model works for different cell types and different stimuli types. Now, looking at all the 108 RGCs I recorded from, we got an excellent quantitative correlation of 0.97 for when we use natural images and 0.89 when I use artificial images. Now, we wanted to look for a difference in the parameters between different cell types and different stimuli types. So we went back and looked at how the distribution shifts for the image projections, and we ran a statistical test to find out that for most of the cells, this curve is statistically linear. So we used linear regression to fit a line to it, and using the slope and intercept parameters for all the curves, we tried to look for differences between the fits. And what we found was that for most of the cells, the slope was greater and the intercept was lower for artificial images. And for none of the cells, the slope was greater and the intercept was greater for natural images. And this is an average of all the fits for natural and artificial images. And you can see that the slope is greater here for artificial images. However, the intercept between the natural and artificial fits is roughly the same. Now, looking at the K and A parameters that we optimized, we found out that there is some dependency between the parameters. So we used the ratio of K over A to represent them, since it showed more fertile result. And in some, for artificial images, the ratio was greater than for natural images, and in general, those RGCs experiencing spike saturation had a lower ratio compared to the rest of the cells. Now, so in conclusion, we developed a model that can predict RGC responses to image stimulation probabilistically. The model overcomes the problem of deterministic models to predict the responses to natural images, and it also holds biophysical meaning with the distribution arising from the structure of the retina and the refractory period taken into account through a spike limiting function. The model parameters optimize slightly differently for different stimuli types, which means that we still have room for improvement, because a perfect model would optimize the same regardless the stimuli. And we are designing new experiments to look into this more deeply. I would like to thank my advisor, Norberto, and my lab members, and I would like to thank you for listening to me.
We have some time for some questions, so just raise your hand if you have any questions.
Can you give intuition about this difference you're seeing between responses to natural and artificial images? I mean, so, in an engineering sense.
Yeah. So I mean, I think that goes back to the responses. Just a second. So you can see that for natural images, you have a lot of quiescent periods, right?
These are strings of unrelated images coming through. I mean, is that correct? From image to image?
It's the same sequence of 30 images.
But the images are not related to each other from one image to the next.
No, they're not temporally correlated. They're not temporally correlated. it's not a movie, it's just a sequence of images. They're presented over 4 times. So you can see that I think that the reason that the model parameters are slightly different is, especially the slope for artificial images, is because the frequency of the response for artificial images is higher than natural images. So that, to me, automatically means that the artificial images have a higher potential to generate a response. However, natural images have a higher potential to generate a greater response, but with lesser frequency.
Do you think if you had used movie, I mean, in other words, you're using natural pictures, but the sequence is not natural.
So
I'm just curious about that choice.
Yeah, so that's what we're trying to do next. We're trying to use natural movies, which are temporally correlated, to see if this might be an adaptation effect or a sublinear units effect, to see if it would change anything about the results we get.
Hi, Nadav.
Hey.
I noticed that there's a common thing between your work and Philip's work, that you're both doing simulations of basically arrays of neurons. And your work, you simulate at the spike level, and the previous one, they're simulating at the neurotransmitter level. So I'm wondering, why do you think it's appropriate for this work that you simulate only at the spike level?
Well, I mean, we know that there is a correlation between the image that I show and the spiking that I get. And essentially the spiking is the signal the brain uses, and simulating at the neurotransmitter level would mean that I would need to be able to characterize how the different neurotransmitters work, and this could be a very interesting thing to do, but it is a different design. It requires a different experimental design.
So you think for the cell type that you're studying is more well characterized at the spike level, so you're going to simulate at that level?
Yeah, it's a black box system essentially, with input in the form of images and outputs in the forms of spikes.
Okay, thanks.
Thank you.
Please, let's all join. Please come together and thank Nadav.